Hello and welcome back to another classic LeetCode problem. We're going to look at LeetCode 146, the LRU cache. Let's read through the problem real quick to understand what we need to do. And then we'll look at a solution. So our task is to design a data structure that follows the constraints of the least recently used LRU cache. And we should implement the LRU cache class in the following way. We need to have a constructor where we specify the capacity, which is a positive size capacity, at least one. And we will have a get method that allows us to return the value associated with a key if it exists. Otherwise, we return -1. We have a put function that allows us to put a key value combination into our least recently used cache. And we update the value of the key if the key exists. Otherwise, add the new key value pair to the cache. If the number of keys exceed the capacity from this operation, evict the least recently used key. So the LRU cache works a little bit like first in, first out. So the oldest element will get evicted when we've reached capacity and we try to add more elements. When we update, when we insert a key that already exists, which means we have an update, in that case, this key will move to let's say, to the, it needs to be removed from the FIFO and be added to it again, anew. So its time to live renews every time it gets updated. That way we maintain that only the least recently used elements are evicted when we run into the cache capacity. And here's an example. So this is how to read this. So the input is we create the cache. This is a constructor with value 2. So only 2 elements can be in the cache. Then we have a put operation, key 1, value 1. So we're putting key 1, value 1 into the cache. Then we have another put operation. We're putting the value and key 2 inside it. Then we call get on key number 1. So we return this value. And now because key number 1 would be the next one to be evicted, but now since we called get, it was used. So we have to move it actually behind the 2, right? So the next time when we run put and we put the element 3 in it, key 3, value 3, it's not that 1 gets evicted, but it's that 2 gets evicted. And that is why now the cache state is 1 and 2. So we have the keys 1 and 2 in the cache. Then we call get again. We call get with 4. It doesn't exist, so we return -1. The state of the LRU cache doesn't change. Now we call put again. Are we putting anything? Putting 3, getting 2. We're getting 2 and 2 doesn't exist. Now we're putting 4. That means the 1 should be evicted. And we end up with 4 and 3. Then we have another get of 1. 1 was evicted, so it's not found. Then we have another get with 3. 3 is in the cache, so it's returned. And the same for the last get, which is the 4, which returns, of course, the value 4. So yeah, that's kind of how the LRU cache works. The challenge of this problem is you need to maintain this kind of queue of items, which would be easy if that's everything. But every time we touch an item in the queue, we kind of need to take it out of the queue and append it to the queue again, anew, right? So that's a challenge here. And this is something that you will have to know after solving this problem, how to do that. And well, how could you implement a data structure that allows you to remove elements from the middle of it? Or any arbitrary elements from it for that matter? Well, the answer is with a linked list. If you, a doubly linked list, so a list where each node has a reference to its predecessor and to its successor. If we have that node, we could remove that node from the list in constant time. If we didn't have that, we would have to traverse the entire array that contains all our elements in our cache and create a new copy of that that excludes the element that we just wanted to remove, which would be highly inefficient. So we're not going to do that. So we need a linked list, but now a linked list doesn't allow a random access to elements, right? If we want to remove an element by a key from a linked list, we have to know which node are we talking about. Otherwise, we have the same problem where we need to traverse the entire list to find that one element that we want to remove. And that is where we need a second data structure. We need a hash map that keeps a reference from all of the keys to the nodes that contain the values that we wrote into the cache. That's pretty much it. Yeah. And that is how we're going to solve this. So we're going to have, well, we need a linked list. And you can start implementing the linked list from the beginning, or you can start just implementing the LRU cache, assuming that you already have a linked list. Both are approaches that you can take, right? But because here you're using two data structures with a hash map and a linked list, it doesn't make sense to overcomplicate it. So I would start here from the low level and just implement a class for list node. And that class would have to have a constructor, right? And that constructor should take maybe the key and the value that we're going to give that list. And it should store that. And self.val as well. And we're going to store exactly, well, we're going to store exactly the key value pairs that we're going to write into our LRU cache. And we need the pointers to the predecessor and the next element. Self.next is none, and self.previous is also none. Now, instead of creating a linked list class, I'm going to integrate this into the LRU cache class. And the first thing is to initialize our cache. So we know that the cache has a fixed capacity size. So we should probably remember what the capacity is so that we can later check of whether we're running over the capacity or not. And we also need our little hash map, right? Maybe we should call this index, or we could call this cache. So the index is to map the keys to the list node. So I will just call it index. Yeah, let's do it like this. So that is that. Now we also need to take care of the initialization of our linked list. Because the LRU cache is going to be empty at some point, I'm thinking that we should probably have a dummy head and a dummy tail element, and that the actual elements inside the cache will be between the head and the tail. There are different ways of how you can implement a linked list, and that is one of those ways. It helps, well, it simplifies the edge cases when you want to remove the last element from the list or the first element from the list, which is exactly what we're going to have to do. We're going to have to insert at the end of the list a new element and remove elements from the middle, but also remove elements from the head of the list if we need to evict one when we're running over capacity. So yeah, we're going to have a head, and we're going to have a head dummy node, list node, I don't know, could be anything. We just call it, I just put 0, -1, -1. And self tail, we do the same. It's really just a dummy value. And then we have to link them together. So the successor of the head is going to be the tail, and the successor, the predecessor of the tail is going to be the head. Tail.pref self.head. So now we've initialized an empty linked list using our list node. Very nice. Okay, so now let's look at the get operation. So the first thing we will check is whether the key exists in our index, right? If key not in, well, if key in index, we're going to do something. Otherwise, we're just going to return -1 as the problem stated beforehand here. So what do we do if the key is in the index? Well, we're going to update it, right? So we will have to get the node that, so we basically have to get, the node, which is index at key. Because remember, we said that we want to have, in our index, we will have basically key to list node mappings. That's what we're going to have in our little index. And yes, this is how we get that node. It could be anywhere in the list, we don't know. So what we'll do now is we're going to remove that node, right? So we will probably need a helper method at some point for that. So remove node, that's what we need to call. And then we actually have to insert that node again into our cache so that it gets appended to the end of our FIFO list. So I'm just going to leave this like this for now, and we can implement those methods in a moment. And then finally, we have to return actually the value, right? So we're just going to return the node.value. So yes, so that's also what we have to do. Let me see. Yes. Now we don't know yet how exactly our remove and insert work, because this node might not exist after we did a remove and an insert. So maybe we should just extract the value right away. So we could do it like this. Yeah, and then we're definitely on the safe side. So get the node and instantly also the value of the node. So, and then we can return the value here. Okay, so next step. What if we do a put operation? Well, a put operation, I think first we have to check the size. Let me see. Well, there's different cases, right? So we have to check if we're running over capacity. We have to check if the key exists, in which case we need to update it, or we just have to insert it. So why don't we start with this check? So if key in self index, right, that means it exists. In that case, we want to remove it again. Node is self.index key. So we're going to remove the node, right? And then we can insert it actually, right? So we can call insert then. So we do, well, let me think about this. Oh, we have to insert the node or a new node new node that we create here. So it's pretty much the same as above here. So we will do that. And then, yeah, and then we have to check if we're running over capacity or not. So if the length of our self index is larger than self capacity, in that case, we need to we need to remove the head of our linked list, right? So we would probably get this with self.head.next, because remember, head is just a dummy and it points to the first element. We know that our capacity is at least 1. So if we, after inserting the node, if we are over capacity, we need to remove 1 element, and it's guaranteed that this exists. Cool. And so we get that node, and then we basically call remove on that node. And we also need to evict the entry in the cache, in the index, right? Because so far we're only removing elements from the linked list, but we don't want to end up with all our keys inside the index, right? Yes. Node.key, right? So we want the key. So in this case, maybe we grab the key right away. So we don't have, so we're not dependent on what the remove method really does. Yes, so now the only thing we need to do is to implement the remove and the insert method. So So let's do that. Remove. And we're going to get the pointer to a node when we call remove, right? So that we can unlink that node. And that is pretty easy. We just store the pointer to the predecessor and the successor of the node. Next is node.pref and node.next. And then we just say node.next is node.pref none. So we remove the pointers from the node to its predecessor and its successor. And we're going to change the successor of the predecessor is next. And next.pref is pref. So yeah, so first we unlink the node, and then we unlink, we cut the links from the node to its predecessor and successor, and then we update the links from the node's old predecessor and from the node's old successor. So, and that effectively removes that node, right? Yes. You probably don't have to do this, but I'd like to do that just to make it clear that this node doesn't have any pointers anywhere anymore. Okay, and so now we can include the remove here. And we can do this here as well, remove. And let me see. The get, we could also express the get as a delete and a put. It's the same. Let me see. Yeah, actually, why don't we do this? I don't understand why we do this. Self.put key val. If we do this, then simply it's going to be removed and then appended again. So yeah, that should simplify it a little bit. But just to be safe, we're going to, yeah, we grab the value here and do this. Okay. Actually, we only need to grab the value here. Yes. Well, actually, we don't even have to do this at all. We just do this. So if the key exists, we're going to update it with its, oh no, yeah, we need to actually get the value. We're going to update it with its existing value. So nothing changes except that the list node gets appended to the end of the FIFO, and then we just return the value. Okay, so now back to the put case, right? So we implemented the remove method. So we removed the node, and now we forget that we had this node at all. Now we need to insert the node. So we need our insert method. Insert self node. Now we could let me think about this. Well, inserting something means we need to insert it at the end, right? So what we have to do is we have to say the predecessor and the next are essentially, well, next is the self.tail. Sorry, next is the self.tail. And the predecessor is basically the predecessor of tail. And now we just say node.previous is predecessor. Node.next is next, which is pointing to tail. And now we need to update the pointers from next.pref is node. And pref.next is also node. I think that should fix it. Yes. So the predecessor of the node that we're going to insert is the last node in the list. The successor of that node is going to be the dummy node, the tail. Node pref is that, yeah, that should all be correct. node.next is next. Ref. Yeah, I think that should be correct. Okay, so now we just need to be careful. So we are reusing a node that already existed. That node already has the correct key. So if we do this, if the key exists, we remove it. Now we need to insert it. So we call self.insert. And it's probably better to create a new node here, because if it's not in the index, we need to do that anyway. So we're going to do a new node. Well, that's what we'll do. So we'll just forget about this node here, really. And yeah, that just removes it. Done. We forget about this object and we create a new object. And that one gets them properly linked. And now we need to take care of this case. So when we need to remove the head, yeah, well, we don't have to really do anything. We just call self.remove on our node, on our first node in our FIFO. So that was a lot of code, a lot of reasoning, and it's quite easy to make mistakes here. It's super easy to make mistakes here. Yes. So let me just go over this one more time to check if the logic works out. We have a list node object that has the key and the value, predecessor, successor. We have our LRU cache that maintains an index that maps from keys to the list node elements. We have a linked list that has a dummy head and a dummy tail. We have, when we remove an element, we get the reference to that element and just link that out. The same for the insert, except for the insert always happens at the end. You can also implement like a remove from top or pop method if you wanted to, but this should just work fine. Now we have the get method. We check if the key is in the index. If it is, we're going to get the node, the list node associated with the key, and return the value from that list node. Now, because we're touching the node, we also need to update it. So it's as if we were writing that value again with the same key. So we're calling the put method. If we don't have the key, we return -1. So now let's look at the logic of the put method. If the key is in the index, that means we will have to remove, well, we have to unlink the associated node. This is what we do here. And then we just insert, well, we remove the node if it exists. And then we insert it as a new node with a new value. So this might have an old value, it just gets removed. And finally, we just check if we are running over capacity. So if the capacity is 1 and we've just inserted the second node, we will pop one node out. So we allow for a brief moment our capacity to go over by 1. And if that is the case, we identify the node that needs to be removed. And that is the successor of the dummy head node. And we also grab the key that belongs to that node. And then we remove the node from the linked list and we remove the key from our index. Yeah, I think that should work. Fingers crossed. Let's see. Okay, val is not defined. Do you mean eval? Self insert list node key val. List node. Let's bring that out. Node equals list node key. Oh, val is not val. Val is value. All right. The next error, if key in index. Well, index doesn't exist. We only have self.index. So that's another mistake that I made. Self.index. Checking. What are all the other index? Yes, they look good. What if we look at access in head or tail? Yeah, it also looks good. So, okay, let's give it one more try. And we're getting the wrong answer. So that means somewhere we have a logic error in our thing. And this is now where it gets nasty, because I was so convinced that we did everything correctly, but we didn't. Yes, def.insert. Oh, we're not updating our index, are we? Right. Def index key should be node. So we missed that. So it expected the values 3 and 4, but it got -1, so it didn't find things. Oh yeah, and it is because the 3 and the 4 were the last two keys that were inserted. So I guess that's why it doesn't find them there. Remove is not defined. Again, I forgot the self. Checking again. Okay, woo. So now we got it. Let's see if there are any edge cases that we missed. All right, so nice. And yeah, so this is a problem that requires a lot of concentration to solve it. You see, I made a lot of small mistakes. So missing updating the index, that was a bigger one. Luckily, I was able to fix them very quickly. And you have to really pay attention how you link and unlink your nodes. Be very careful with reusing nodes. It's probably better to throw them away and create new ones. Otherwise, you might get weird side effects that make debugging absolutely impossible. Yes, and try to reuse functionality that you already implemented, like the remove and the inserting that we use multiple times. And to be honest, so this is one of the problems where I had a lot of attempts in the past to get it right, and it was a pain. You know, I tried implementations where I had my own list, a linked list object, not just a list node that would handle the inserts and removals for me. It's just painful. So you have to practice this one maybe a couple of times, and also look at different list implementations to really understand what this code should look like. And yeah, this is one of those problems that is really cool when you can solve it and when you understand how to solve it. So yeah, happy coding.